So we are starting our last lesson for this particular unit, Unit 8, which was all about the equations of lines and planes. We've covered the equations of lines in R2 and R3, and so far we've covered the vector and parametric equation of a plane. And what we're going to do today is look at the Cartesian equation of a plane. So we've talked about already that we use pi to represent a plane. So here's my general plane in R3. There's going to be one line perpendicular to that plane that we can draw through the origin. And we're going to call that the normal axis. So let me see if I can just spin that a little just so that we can get, oh, that was a pretty good view back there. Let me show the controllers. Back it up this way a little bit. So that axis right here, that is the normal axis passing through the origin perpendicular to the plane. It's parallel to this one right here. We can create a normal by joining the origin to any point in the normal, just as we did before, any point on the normal axis, I mean. The vector for the normal is now going to be A, comma B, comma C. In general, a normal is going to be any line which is perpendicular to the plane. So there's my normal there. All normals will be parallel. This just so happens to be the normal axis because it passes through the origin. Again, it's as a vector, it's going to have its tail at the origin and its tip at A, B, C, which is any point along the normal axis. Now we're going to think about the Cartesian equation of a plane. And we're going to try to derive it the same way we did for the Cartesian equation of a line in R2 when we did that. So we've got a general point on the line, x naught, y naught, z naught. Here is our normal axis. It's coming through the origin, passing so that it's perpendicular to the plane. This is a general point on my plane, so this can be anywhere on the plane. And notice how the normal axis is perpendicular to the plane. So what we're going to do now is we're going to extend what we did before. The normal is perpendicular to this red vector here. That means the dot product of these two should be 0. So we're going to start with the normal, which we said was A, B, C. P naught, P0 can be found by translating the tail to the origin, which means subtract x naught, subtract y naught, and I'm going to subtract z naught from there. So the vector P naught P is going to be written as x minus x naught, y minus y naught, and z minus z naught. Since the normal is perpendicular, as I've already mentioned, the dot product of the normal with this vector here, P naught P, is going to be 0. So we're going to be doing A, B, C, dot x minus x naught, y minus y naught, z minus z naught. So we're going to multiply the x components, x times this, b times that, c times that. Expanding ax minus ax naught, plus by minus by naught, plus cz minus cz naught. And then what I'm going to do is I'm going to group the Cartesian variables together, x, y, and z. I'm remembering, of course, that x naught, y naught, and z naught are unknown constants, but they are constants. So when we group them all together, what we're going to find out is that this here, which I've written off to the side, negative ax naught, negative by naught, negative c z naught, it's a constant, so I can replace it with the letter d. And that gives me this equation right here on the bottom, ax plus by plus cz plus d, which is the Cartesian equation of a line. All right, moving on to the next slide, we're going to summarize that now. So the Cartesian equation of a line in R3 is now given by all three of our Cartesian variables in R3. Ax plus by plus cz plus d equals 0. The normal to my plane is going to be A, comma B, comma C. And remember how you find a normal to a plane. What you need to do is take the cross product of any two non-collinear direction vectors on the plane. All right, suppose my normal to my plane is 2, 6, negative 4. What are other different normals to the plane? So there is the normal. Is this one normal now? Let's spin this right now and take a look. So now you can see that that purple one is not normal to the plane. If I want the purple one to be normal to the plane, then what could I do? If I call this -4, then this would need to be -12, and this would need to be +8. And now let's spin this around, and now you can see right there, you could tell from that angle right there that it is now perpendicular to the plane. So let's reset this. Are there other normals to the plane? Absolutely, there are. There's really an infinite number, and I'm just going to write it this way. K times 6, or 2, 6, -4, where K is any real number. Those will all be normals to the plane. So there's, in fact, this normal is not even in simplest form, because we could have written it as 1, 3, -2. So again, infinite number of normals, all scalar multiples of this normal, written in simplest form. What's true about the normals for two parallel planes? So I've got two planes here. They are parallel. I'm going to set that down so I can spin. And what's true about the normals? So we've got our visual happening there where we could see. And now we can see our normals are 2, 6, -4, 1, 3, and -2. And what we can see is that they're scalar multiples of each other. So if I wanted to see if planes were parallel, I could check their normals. If the normals are scalar multiples for some k not equal to 0, then the two planes are parallel. Now, think about this. So if you grab your desk, think about your desk, or maybe the whiteboards, if we had the whiteboards. You put a normal on that. Now, just because two normals are parallel does not mean that the planes are parallel, because we've already established, not two normals, sorry, two direction vectors I'm thinking about. So we've already established that if we have one line, there's an infinite number of planes that could spin around that. So just because you demonstrate that direction vectors are parallel to each other or scalar multiples, that doesn't necessarily make the planes parallel. However, if we have the normal, so what we're going to see now is to decide if planes are parallel or perpendicular, we are never going to use direction vectors. What we're going to use is normals. There is absolutely only one normal to the plane in terms of simplified form. Every other normal would be a scalar multiple of that, whereas we would have an infinite number of direction vectors. How many different pencils can you lie on a plane? So we're not going to compare them. Now, what would be true about the normals for two planes that are perpendicular? So let's spin these axes around just so you can see the two normals. We can definitely see that the normals are perpendicular if the planes are perpendicular. Let that spin again just so that you could see there. So if the planes are perpendicular, the normals are perpendicular. But we do know that if two vectors are perpendicular, then the dot product has to be 0. So if normal 1 dot normal 2 is 0, we do now know that those planes would be perpendicular. And then I've shown on the bottom, if we take the dot product, 2 times -5 is -10, plus 18 minus 8 is going to give us 0. D is our constant. It is not part of the normal. How would you find an angle between planes? Again, we're not going to use direction vectors. The angles between two direction vectors won't give you the angles between the planes because there's an infinite number of them. There is only two normals to a plane, so the angle between the planes can be given by the normals. And a reminder that to find the angle, we rearrange our dot product formula. So we'll say that cos theta is normal 1 dot normal 2 divided by the magnitude of normal 1 times the magnitude of normal 2. All right, and now that we've covered the basics, we're going to try and do some example problems here. So find the Cartesian equation of a plane passing through 5, -3, 2, which has -2, 7, 1 as a normal. So the first thing we're going to remember is what was the Cartesian equation of the plane? It was ax plus by plus cz plus d is equal to 0. The normal to the plane will tell us what a, b, and c should be. So we know the normal is -2, 7, and 1. So I now know that A is -2, B is 7, and C is 1. I will now plug those in to my equation. I will get -2x plus 7y plus z plus d is 0. How do we find d? We will find d by plugging the coordinates from the given point, 5, -3, 2, into this equation. So we've got that point. We need to plug that into the equation. -2 times 5, 7 times -3, plus 2 plus d is 0. We'll now be able to find d. We're going to get -10 minus 21 is -31, plus 2 is -29. So now -29 plus d is 0. That gives me that d is 29. And now back to the equation. The equation should be -2x plus 7y plus z equals -29. Now, I would have put plus d here, so if we want to, so that's not confusing, we could also write it this way, plus 29 equals 0. I chose to write the constant on the other side. So either of these would be appropriate. All right, so that's example 1, sort of straightforward, very similar to the one we did when we found the Cartesian equation of a line in R2. Example 2, find the Cartesian form or the Cartesian equation of a plane that has this for its vector equation. What would be the best way to solve this? All right, so the Cartesian equation of a plane requires that we have the normal. And so that if we just think about here, we have a plane sitting like this. I need its normal. So there's the normal. It's going to meet here at 90 degrees. Now, this normal will be perpendicular to any direction vector on a plane. So there's one direction vector. There is a second direction vector. So that's D1. And this one's D2. Notice how the normal is perpendicular to both of these. So what does that mean? The cross product of these two direction vectors should be able to give me the normal because each of them creates a vector that is perpendicular to both. So I believe we learned that in Unit 7. I just want to drop that pen now. And let's just show you what I'm talking about. The normal is perpendicular to the direction vector. The cross product of the two direction vectors will determine the normal to the plane. So what we're going to do now is trying to figure out how we would do that. So remember to find the cross product. Let me just see which way I've done it over here. So I'm going to do 0, 1, 2 cross -2, 1, 5. So we're going to do y, z, x, back to y, y, z, x, back to y. And then what we're going to do is, well, I'll show you that over here as well. I'm going to do 5. 1 times 5 is 5. 2 times 1 is 2. So we're going to have 5 minus 2. That'll give us a 3 here. Now we're going to have 2 times -2 is -4. And 0 times 5 is 0. And -4 minus 0 is -4. That's how we got that one. And for the last one, 0 times 1 is 0. 1 times -2 is -2. 0 take away -2 is +2. So I now have the cross product is 3, -4, 2, and that gives me the normal to the plane. How do I know that? This vector here is perpendicular to both of these two vectors, also perpendicular to the plane. So now we will continue this question very similar to the previous one. We've now made it like the previous one. We have the normal now. And we have a point on the plane. So it's simply just a matter of plugging in and finishing off. So 3x plus, or not 3x, plus 3x minus 4y plus 2z plus d equals 0. Plugging in an a of 3, a b of -4, and a c of +2. We will now plug in the coordinates of the point 1, 3, 1 to find d. So 1, 3, 1 is on the plane. 3 times 1 minus 4 times 3 plus 2 times 1 plus d is 0. That's going to give 3 minus 12 plus 2. So 3 plus 2 is 5. 5 minus 12 is -7. -7 plus d is 0. That's going to give us that d is 7. And plugging that back into there, we now are going to have 3x minus 4y plus 2z plus 7 is 0. Alternately, as I had done on the previous example, we could also write equals -7. if we choose to write it that way. All right, so that's example 2. Fastest way to find the Cartesian equation of the plane is simply to take the cross product of the two direction vectors, which gives you a normal, and then substitute the point in to find the constant for the plane. All right, let's move on to example 3. Show that these two planes are perpendicular to each other. Well, let's just start with A. How are you going to show that those two planes are perpendicular to each other? So if we remember, if you're going to compare whether or not planes are parallel or perpendicular, we should not be using direction vectors because, as I mentioned, there's an infinite number of direction vectors, and just because I find two direction vectors that are perpendicular is not going to make the planes perpendicular. So we're going to compare the normals. Normal 1 is 2, negative 3, positive 1. Normal 2 is 4, negative 3, negative 17. And then I simply need to take the dot product of those two and see if I get 0 back. So let's see what that looks like. Normal 1 is 2, negative 3, 1, as I mentioned. Normal 2 is 4, negative 3, negative 17. I need to take the cross, not the cross. I did say the cross, but I really meant the dot. The dot product of those two. If the dot product is 0, the two normals are perpendicular. Remember what the cross product does. It returns a vector, a third vector that's perpendicular to two others. So again, I want to check to see if the dot product is 0. The cross product cannot be 0. The cross product could be the 0 vector, but it can never be the number 0. So I'm going to have 2 times 4, negative 3 times negative 3. Or no, let's write it this way. 2 times 4 plus negative 3 times negative 3 plus 1 times negative 17. That's going to give me 4. 2 times 4 is 8. So I get 8 plus 9 minus 17. 8 plus 9 is 17. 17 minus 17 is 0. The dot product is 0. So now we should make our conclusion. So let me copy that line. And let's just say, since the dot product is 0, the normals are perpendicular, so the planes, now you see how bit of a typist I am, the planes are perpendicular. All right, so that one wasn't too bad. Thankfully, they gave it to us in Cartesian form. Now the second question, they're giving us plane pi 1 in vector form, and plane pi 2 is in vector form. And they're asking us to decide, are they parallel but not coincident? So the problem now in this particular question is we cannot do this by comparing direction vectors, because infinite number of direction vectors, and just because I found a pairing where they were scalar multiples of each other would not make the planes parallel. So what do we need to do? All right, so as in the previous question here, well, we're going to do exactly what we did here. We are going to take the cross product of the two direction vectors. That will return a vector perpendicular to both, but because those vectors both lie on the plane, the vector it returns will in fact be the normal. So what we're going to need to do, take the cross product. Well, we're going to compare the normals rather than the direction vectors. So I'm going to use the direction vectors to find the normals, and specifically I'm going to take the cross product. So I will show you, because I don't have that typed over here. So let's, for the first plane, look at 0, negative 2, 2, 0. And the second plane, or the second direction vector on the first plane is 2, 3, 0, back to 2. I just want to make sure I'm correct now. So I am starting with 0 to negative 2 to 2 to 0, 2 to 3 to 0 to 2. Now if we do the cross product, we're going to be 0 take away negative 4, which is positive 4. Multiply those two, 0. Multiply those two, 0 take away 6 is negative 6. Multiply those two, 4. 4 take away 0 is 4. So there is normal number 1. Let's look at normal 2. Again, we're going to have 2, negative 2, 5, back to 2. Then we have 4, 4, 2, back to 4. I'm just going to double check to make sure that that is correct. Start with the y component, 2 to negative 2 to 5, back to 2, 4 to 4 to 2, back to 4. So when we do the cross for the x component, we are going to get 8, take away negative 8, which should be 16. Then we're going to get negative 4, take away 20, which is negative 24. Hopefully I'm doing my math correct here. And now we will get 5 times 4, which is 20, take away 2 times 2, so 20. Take away 4 is 16. Let's drop that, and hopefully I've made no errors there. So we have 16, negative 24, 16. I did not simplify these, but I suppose we could have, right? Written the vectors in simplest form. I'm just going to leave them where they are right now, because I'm going to notice if I multiply normal 1 by 4, I will get normal 2. So normal 2 is 4 times normal 1. 4 times 4 is 16. Negative 6 times 4 is negative 24. 4 times 4 is 16. So we now know the planes are parallel. The next thing you have to determine is, are these planes coincident? So what we're going to think about here is we need them to share a point in common for them to be coincident. So the points we are given are this point here, 0, 0, 2. And look what I'm given over here. I'm given the point 0, 0, negative 3. So if the x and y coordinates are equal and the z coordinates are different, there is no way these planes can be the same plane. If 0, 0, 2 is on this plane, then 0, 0, 2 should be on this plane, but we're getting 0, 0, negative 3. So these planes are definitely parallel, but not coincident. There would be, as I mentioned, one shared value for 0, 0. You'd get 0, 0 shared same value, but we're getting 2 different values back. So these 2 planes are parallel, but not coincident. Another way to demonstrate this, but I'm not going to do this here, would be now that you have the normal, you could plug the point in to find the Cartesian equation. All right, I just had to clear my throat there. So what we could do is we could find the Cartesian equation. We have 4x minus 6y plus 4z plus d. Plug in 0, 0, 2 to find the Cartesian equation. Do the same with this one. You could actually simplify these normals down too if you wanted to. And then you would notice that the planes would not be scalar multiples of each other. All right, so I thought I quickly would show that to you rather than just speaking about it. That favors auditory learners, not the visual. So here we go. I've determined the Cartesian equation using the normal, and then because we have 0, 0, 2, 4 times 2 plus d is 0, d is negative 8. Plugging that back in, 4x minus 6y plus 4z minus 8 is 0, divided by 2. 2x minus 3y plus 2z minus 4 is 0. That's Cartesian equation number 1. Cartesian equation number 2, plugging in the normal, 16x minus 24y plus 16z plus d is 0. Again, x and y are both 0, so I'm just going to get 16 times negative 3 plus d is 0. d is 48. Plugging back in, 16x minus 24y plus 16z plus 48 is 0. Now we're going to divide by 8. I'll get 2x minus 3y plus 2z plus 6 is equal to 0. And then when you compare those 2 Cartesian equations now, you can see they differ by a constant, so they're definitely parallel and non-coincident. All right, end of example 3, now on to example 4. Determine the Cartesian, it says Cartesian and parametric equations of the plane that contain the point negative 1, 1, 0, and it's perpendicular to the line joining the points 1, 2, 1, and 3, negative 2, 0. All right, so for you to get a feel about what this question is talking about, so take a piece of paper, put a dot on that piece of paper to represent negative 1, 1, 0. So there is your plane. It has the point negative 1, 1, 0 on it. Now that plane needs to be held perpendicular to a line that's joining the points 1, 2, 1, and 3, negative 2, 0. So hold a pencil to that line, and what do you notice about the line? And maybe I'll just spin these axes a little bit just so that you can see what I'm talking about. Show the controller so I can get that in a better position. All right, so there is our plane. There's our pencil being held to the plane so that it's perpendicular. This red line is the line connecting those 2 points. And if it's perpendicular to the plane, that means that must be the normal to the plane. So the first thing we could do is it's going to be very straightforward to find the Cartesian equation of this particular plane, because I'm just going to find the direction vector for the line. So that's where I'm going to start. The direction vector for the line is normal to the plane. So starting with the direction vector, which is also the normal, we go from 1 to 3, that's 2. From 2 to -2 is -4. And from 1 to 0 is -1. So the direction vector for this line is 2, -4, -1. That makes it the normal to the plane. So we can go back to our Cartesian equation now. This will be the third time we've done this in this particular lesson. 2x plus 4y minus z plus d is 0. And now let's think about it. We've got to use the correct point, though. Are these points on the plane? It doesn't tell us they are. It says they're on the line. We have no guarantee that they're on the plane, so what we're going to do is use this point here. The point -1, 1, 0 is definitely on the plane. So we will now plug that in. 2 times -1 minus 4 times 1 plus 0 or minus 0 plus d is 0. That's going to give us -2 minus 4, which is -6. So -6 is d, which gives us that -6 plus d, sorry, is equal to 0. That gives us that d is 6. I can now plug that back in and get 2x minus 4y minus z plus 6 is 0. That's the scalar equation. Now, that was straightforward. Let's show, well, no, I don't want to show that one just yet. But how are we going to find the parametric equations? That's step 2. All right, so the simplest way to do it would be to remember that the Cartesian. Remember that the parametric and vector equations of a plane need 2 parameters. That will be my starting point. So a plane has 2 parameters, so arbitrarily I'm going to allow x to be s and y to be t. Then I'm going to plug into this equation to get a so here's my parametric equation for x is s, and y is t. I'm now going to work the Cartesian equation of the plane, I'm tongue-tied right now, to figure out what z needs to be. So 2s minus 4t minus z plus 6 equals 0, and that gives me that z is equal to 6 plus 2s minus 4t. So I have my 3 parametric equations. I have s, really if we want, I have 0 plus s plus 0t. Here I have 0 plus 0s plus t. Here I have 6 plus 2s minus 4t. So there's the parametric, and if I want to convert that to a vector equation, I can do that next. So writing them this way so that it's clearer, here are our 3 parametric equations: x equals s, y equals t, z equals 6 plus 2s minus 4t. I do have to state that s and t are any real numbers. Then we can go to the vector equation. So the point now is going to be 0, 0, 6. The direction vector for s is going to be 1, 0, 2. The direction vector for t is going to be 0, 1, -4. And if you like to make it clearer, I could write 0 plus s plus 0t. And here I can write 0 plus 0s plus t. And then that will make it clearer where these come from: 0, 0, 6, 1, 0, 2, 0, 1, -4. Now I'm going to show you alternate ways to do it, because you might say, well, why did you pick x is s and y is t? The reason I did that over here was because the coefficient for z is 1. I wasn't going to have to work with fractions. But let's show you what it would look like if we did something a bit different. We could allow y to be s, we could allow z to be t. So plugging into the equation, we would get 2x minus 4s minus t plus 6 is 0. I get 2x is negative 6 plus 4s minus t. And now I'm going to divide by 2. I will get negative 3 plus 2s plus 0.5t. That's the parametric equation for x now. Remember we said y was s and z was t. So now in terms of our point, we are negative 3, 0, 0. In terms of s, we are 2, 1, 0. In terms of t, we're 0.50 and 1. So this is an alternate equation. Now, we did say we don't want there to be decimals in these, so what I'm going to do is double this and get 1, 0, 2 to get rid of the decimals. So that's an alternate vector equation. Now we can come over here, and what happens if we let x be s and z be t? Then I'm going to get 2s minus 4y minus t plus s is 0. 4y to this side, I'm going to get 6 plus 2s minus t. And now we have x is s. I divide everything by 4. I get 1.5 plus 0.5 minus 0.25t. And of course, the other parametric equation was z is t. So for the point, we are 0, 1.50. For s, we are 1, 0.5, and 0. For t, we are 0, negative 0.25, and 1. That's where those have come from. And now I'm going to clean this up. I don't want that decimal value there, so multiply by 2, 2, 1, 0. I don't want the decimal value here, so I'm going to multiply by 4, 0, negative 1, 4. You cannot multiply the point. Remember, that's a point in space. You do not want to multiply that to take out the decimals. It's not a direction vector. It's an actual point in space, so it has to stay where it is. So those are our three options. Personally, I think this one was the easiest because I did not need to divide. And in this particular case, I created fractional values or decimal values for my direction vector. All right, so there's an alternate way to do it. This is the easiest way to do it, is just to remember or recall that a plane has two parameters, s and t, and you allow one Cartesian variable to be s and allow another one to be t. The other way to do it, I'm going to show you on this slide, is to find 3 points. If you have 3 points, then you can find the direction vectors from the 3 points. So what I could do is just arbitrarily to find the points. We have 1 point, negative 1, 1, 0. To find another point, I just arbitrarily choose. I choose x to be 2 and y to be 1. When I plug that into the Cartesian equation, I get 2 times 2 minus 4 times 1 plus 6, bringing z over to this side. I will get 4 minus 4 plus 6, so z is 6. So the point 2, 1, 6 is on the line. Alternately, now I'm choosing x is negative 2 and y is 3. I get 2 times negative 2 minus 4 times 3 plus 6. That gives me negative 4 minus 12, negative 16 plus 6 is negative 10. So negative 2, 3, negative 10 is another point on the line. So, and then what I'm after are some direction vectors. So direction vector. Let me see what order I was doing these in. So we're going from this point to that point. So negative 1 to 2 is plus 3. 1 to 1 is no change, so that's 0. 0 to 6 is 6. So the direction vector from this point to that point is 3, 0, 6. The direction vector from this point to this point would become negative 1 to negative 2 is minus 1. 1 to 3 is plus 2. 0 to negative 10 is minus 10. So the direction vector there would be negative 1, 2, comma, negative 10. Now I have my two direction vectors. And I want to come over here and write, well, right over here I am writing, it did say parametric, but I'm writing a vector equation here. Vector equation, my point, I'm picking this point, but I could have chosen any one of those two. And now I'm going to plug in my direction vector, negative 1, 2, negative 10. If I want to be sticky about minimizing the number of negatives, I probably should be writing that as 1, negative 2, positive 10. and the other direction vector 3, 0, 6. But again, if we want to be stick to the parameters in class that we talked about for writing these, we probably should write that as 1, 0, 2. So I'm going to copy this and paste it, and beneath that write that, minimize the negatives. So I'm following the rules I'm telling you to follow, and then divide that by 3. And then parametrically, we would be negative x equals negative 1 plus s plus t, y equals 1 minus 2s, and z is equal to 10s plus 2t. Now, if I want to check just to make sure these are correct, we could take the cross product. Here what I've done is I've got my direction vectors here by putting in 2 points that are on the plane. So I just wanted to come over here and fix this. So the points we have, negative 1, 1, 0, 2, 1, 6. And then I'm getting my direction vectors, and then I'm going to take the cross product of my 2 direction vectors. All right, I'm going to try that again. I have for my first point, negative 1, 1. Plugging into the equation, I found that Z1 was 0. 2, 1, we find that Z2 is 6. Plugging in our last point, I got to fix this one up. It should be negative 2. This one should have been 3. And we now have that Z is negative 10. We get our 2 direction vectors, 3, 0, 6. And our second direction vector, I'm not sure how I'm doing this one. I didn't do it the same way I did here because I'm going between these 2 points, from this point to that point. That's different from what I did there. But if I did that, I would get this direction vector, negative 4, 2, negative 16. And then I want to show you what would happen. Here's the key. This is the cross product of those 2 vectors. And notice what the cross product returns. It should return a vector perpendicular to both, i.e. the normal. So is this the normal vector? So here we are here, 2, negative 4, negative 1. So if we times this by negative 6, we get negative 12. Times by negative 6, we get 24. Times by negative 6, we get positive 6. So this is definitely the normal to the plane. And if I back up to this example over here quickly and I show my normal vector check, my direction vectors that we are looking at, we've got lots of direction vectors we could pick. I've got 1, 0, 2. I have 0, negative 1, 4. When I take the cross product of those, it returns negative 2, 4, 1. That's definitely a scalar multiple of that normal. Let's try a different one. 1, 0, 2. We've got 2, 1, 0. That's another potential one. So let's put 2, 1, 0. That's the last one I'm going to check there. And I get negative 2, 4, 1, which again is a scalar multiple of the direction vector. So if you have the Cartesian equation and you've been asked to find a parametric or a vector equation, once you found your direction vectors, time permitting, take the cross product of those 2 direction vectors and ensure that what you get back is a scalar multiple of the normal. All right, now I just want to jump back to here. So I did say on the previous lesson, we found the equation of, we were trying to find the points A, B. I'm not sure if you remember doing this particular one. So this was our plane, and we decided when you intersect the x and y axis, we would be 0, y, 0. We would be 0, 0, z for this one. And then we plugged into the parametric equations and we tried to solve 2 systems and 2 unknowns. So here's a different way to think about it now. I can convert this to Cartesian form by taking the cross product of those 2 vectors. So if I cross those 2 vectors, again, I've just plugged into the formula, but I am not very good at remembering what that formula is. I prefer to do my crossing this way. 1, 2. The other one is negative 1, 1, 3, 1. And I'm going to get 2 times 1 is 2. 5. Let me just make sure I did this right. All right, I just went back just to make sure I wrote that correctly. I have these two in the reverse order. So just showing you that this is correct. Y to Z to X back to Y. We are Y to Z to X back to Y. Cross product, 2 times 3 is 6. Take away, 5 times 1 is negative 5. 6 take away negative 5, positive 11. 5 times 1 is 5. 1 times 3 is 3. 5 take away 3 is 2. 1 times negative 1 is negative 1, and 2 times 1 is 2, and negative 1 minus 2 is negative 3. So that gives me the normal at 11 to negative 3. Now what I'm going to do is find that Cartesian equation. I know it is 11x plus 2y minus 3z. I'm now going to plug in the point 1, 2, 3. 11 times 1 plus 2 times 2 minus 3 times 3 plus d. That gives us 11 plus 4 is 15 minus 9 is 6. 6 plus d is 0, so d is negative 6. There is my Cartesian equation. 11x plus 2y minus 3z minus 6 equals 0. Now once we've done that, yes, it is a bit of work to find the cross product, and in my case I had those flipped, so I would have the wrong cross product. I possibly could check that I am, well, I can't even check that I'm right because I've used that one point. I would need another point on the plane. What we're going to do now is find the x and y intercepts. Much easier to do it now. I don't have to solve a linear system of two equations and two unknowns, m and m, as we did before. So to find the y-intercept, it's simply, I'm looking for 0, a 0. So I'm going to come into the Cartesian equation. That becomes 0, that becomes 0. I'm now solving 2y minus 6 equals 0. And that gives me 2y is 6, so y is 3. I think this is much faster than solving that linear system from the previous lesson. And now we're going to be 0, 0, comma b. And we plug in a 0 here and a 0 here, we will be left with negative 3z minus 6 is 0. So negative 3z is 6, z is negative 2. I now have my 2 points. I think that was much faster. It's going to end the same way that it did before. Again, those two should be positive. I'm just going to go open the other file. All right, so this is what we did in the previous lesson where we said that the x and, well, for the y-intercept, we said that x is 0, z is 0, and then we solved that linear system. For the z-intercept, we've now said that x is 0 and y is 0, and we solved that linear system. Look at all of that work we had to do. Contrast that with how simple it was here to find the y-intercept, how simple it was to find the z-intercept. So the faster way to do this, of course, was to take the cross product, find the Cartesian equation of the plane, and go from there. And again, usually I say in university, time will be your enemy. If there's a faster, more efficient way to solve a problem, that's the method you should choose. All right, so that brings us to the end of our last lesson in Unit 8. Just going to bump back to show you the key ideas. If you want to find the angles between two planes, we're going to use the normals because there's only one normal, and I am talking about all scalar multiples of that one normal, but all the normals are parallel. So it's okay to compare the normals. If we want to see if planes are perpendicular, dot product of the normals. If we want to see if they're parallel, are the normals scalar multiples of each other. And then our other big idea was there's the Cartesian equation of the plane, and the Cartesian equation of the plane gives us the normals. If they give me vector equations of the planes, I will take the cross product to find the normal and make my comparisons that way. All right, that is the end of Lesson 5. If you made it to the end, once again, thank you for watching. Don't forget to like and subscribe. Stay tuned for Unit 9, which is our last unit, and as always, take care.